the weird things you find out when you try to make old technology work for you. But it looks like we're all set up, ready to start. Welcome back, everyone. So for today's class, we're making the jump from section 2.3 to taking the limits without having to rely on a graph using the limit laws, the so-called algebraic methods. So we're not quite done with 2.3. We're going to go back in, finish this one off, but we should finish it today. The due date then is a 1 week turnaround, January 29th. Also, whenever you see these kinds of files like these here, anything that's been indented, or certainly it says review for sure, but those are always going to be considered optional reading. I would definitely, as a student, take a look at it. The purpose of throwing in those files is just a quick one-stop shop for any review material we're about to cover. It's indented over 2.4, suggesting it's really good review material for that section in particular. Well, other things I want to say before we get started is, in WebAssign, if we go back to the student view on our WebAssign, I want to mention a couple things about the homework itself that folks have found. If you go to, say, any one of these sections, let's take a look at 2.4. There it goes. It's a little bit slow today. Let me undo that annotate. Then on these kinds of problems, you'll notice that there's a button called Practice Another Version. It's a really cool button. It means you can review problems right here in WebAssign if you wanted to, studying for exam. I give additional problems aside from that. But if you click on this, it's another one of those situations where it just depends. Some of the problems really do have another version, and you can work on another one without any stakes affecting your score. But as you go through here, you might find some that do not have a second version, like this one. There's not even an option of practice another version. And occasionally, even if this button is live, you can click it, and it might say, not on this one, but it might say, there is no additional versions to practice. That's kind of frustrating. I'm going to try to look at the problems I'm assigning going forward in the upcoming sections and try to go for the problems that have multiple versions in case you want to study that way. But there is some sections where I've noticed my hands are kind of tied. The actual problems you want to assign, the ones that are good that line up with the notes, are not necessarily the ones that have a lot of versions to go with it, unfortunately. But that's definitely a good option. If you decide you want to practice more problems, but maybe you couldn't, they didn't give us multiple versions, you could also take this approach. Go to My eBooks. Let's suppose we're practicing a problem in 2.4. So this is our actual online textbook. And go to, we're in chapter 2. Move that out of the way. That is not where I want to be. Click on this right here, the index, I suppose is what that is. We're in 2.4, but we're just trying to practice additional problems. Go to the 2.4 exercises right here. And because it's an online text, this is actually a pretty great resource for studying additional problems. It's all of the problems in the text, so some of them might not be questions you'd really want to take a look at, but you'll be able to identify which ones are similar to the ones we actually did. So if we scroll down, you know what, we might have done one very similar to that, or we're about to do. But maybe you're wanting to practice things like these, doing limits. These are excellent problems. And there's answers to the odd ones right down below that you can reference right away to get immediate feedback if you're on the right track or not. So this is an additional resource when the practice another version fails you in WebAssign. There's still plenty of problems in the book itself. Well, any other questions, folks, about that issues with WebAssign? Okay, well, let's take a look where we're at so far. I have an actual list of announcements I want to make sure I got to today. Okay, so we showed that. And last thing I want to mention is, let's go back to the Moodle website. Now that the course really got kicked off, it's really going, we're in week 3. Right up at the top, under grades, you'll start to notice that this is going to be updated usually about twice a week, possibly a little bit more depending on what's going on in the week. I'll be updating your grade, pulling in your WebAssign grade, usually on Thursday or Friday. And anytime I grade anything, say your upcoming quiz, I'll also update your entire grade set segment up there, including the WebAssign. And I'll start soon posting something called a course grade, telling you where you're at in the course at any given time. Your grade updates all the time. You can click up here to see where you're at. or send me an email at any time if you have a grade question. I'm doing my grades on a separate Excel spreadsheet. I might just share that spreadsheet, your row, if there's a grade question. And everything I do here, I just upload the results from my spreadsheet. Well, I think that's my announcement so far, folks. Any other questions or comments that you want to discuss before we start? Okay, well, let's get going then. We are still in section 2.3, but we're nearly done with it. The purpose of 2.3 is we're trying to get a picture in our mind of what does a limit look like when it's dealing with finite numbers. So loads of pictures in 2.3, and then we'll do it more exactly in section 2.4. I turn to this just as a good reminder, as a good refresher over the weekend. When you go to take the limit, if it says x tends towards a, that means you're heading towards a specific finite number, like say maybe a is 1 in this problem. But whenever you take that limit, the value at a is irrelevant. You take x close to a on either side of a if it's a double-sided limit like this one. But whatever happens at a makes no difference to the outcome of the limit. That's one thing that's really weird. A limit cannot be changed based off of one single point. You have to change the entire curve to start messing with the limit. Well, we took a look at these kinds of limits. Then after that, it was more practice with graphs, things with single-sided limits, limits where we go off to infinity, like in these cases. And this was our last problem before we called, was it? Yes, it was the last problem before we called it a night. Just practicing looking at generic limits. Say, for example, this is a limit as x tends towards 2. So what you do when you see that is go towards 2 on the horizontal axis. We're here. Well, the function is going down towards negative infinity, so that was our output on that one. And that's essentially the name of the game. We're looking at limits, conflating them with graphs, so we get a mental intuition, and we'll be in great shape in the next section. But one thing that is kind of tricky about this is it's easier to take a graph and simplify the limits, say what they should equate to. It's harder to have the limits and find a candidate graph that satisfies all the information. So that's our next problem that we'll practice. Let's take extra care on this one. First thing we should mention, maybe right even right before the exercise, is just some review information about functions. A function y equals f of x satisfies the vertical line test. So because we're plotting a function, we too have to ensure our function passes that vertical line test. And just as a reminder, passing the vertical line test means the following. Let's put maybe a colon here. The vertical line test says any, let me spell any right first, any vertical line intersects the graph at most once. The moment it hits it twice or multiple times, say on this graph right here, we've got a problem. This would never be the graph of a function. Since there are some vertical lines that are non-problematic, that one intersects exactly once. But over here, it's intersected the graph 3 different times. No function could actually give this kind of behavior with just a single independent variable x. So those are the kinds of things that we're trying to avoid for our graph. We want one curve that's going to satisfy all that information right here, but also pass the vertical line test. Oh, let me get rid of that, and let's get started. But first, any questions at all or clarifications on the vertical line test? Okay, maybe just for a quick visual, take a look at a graph, say right here before we pop down. This one passes the vertical line test only because of that open circle right there. But if you fill that in, say in this location, it fails the vertical line test right away, and this entire problem is a lie. There is no function here, and so all the limit statements we're making no longer make sense. It was actually very critical that there's a solid dot, exactly one solid dot, on this vertical line segment. put another, say, solid dot right here, same problem. A vertical line intersects, I missed. A vertical line would intersect twice. Does that make sense to folks? Does that make sense to folks on those issues there for this graph? Okay, mainly mentioning that because sometimes failing the vertical line test, it's not really easy to see. It could be some small issue like here. All right, let's go down now, and we're going to officially work through this problem. So first thing we want to do is, well, we're sketching an example of some function. It's sometimes a good idea to emphasize the horizontal axis a little bit more than the vertical axis for this type of situation. Now we'll start looking at the actual values. This is all temporary highlighting, but I usually like to look at these values in particular. I'll take off that highlighting in a moment, but the reason I'm looking at these are, it's telling me all along the x-axis where all the interesting stuff is actually going to occur. So we know there's going to be something at 0. We'll have single-sided limits around 0, something going off to a negative infinity, and something on 4. I'll actually put something here. 1, 2, 3, 4. That'll do the job. That's 4 to the left, 4 to the right, and something else at positive infinity. So as far as the horizontal axes go, pretty much this is about all I need. We also have values right here on the origin, so I couldn't put a tick mark there. Next thing to take a look at is all of these outputs. Outputs to the function, outputs to the limits, whether they're values that existed or not. These are all good to look at. Essentially what we're doing is we're looking before we leap. That's good in math as it is in real life. So f at 0 at 3 means we should have 1, 2, 3, something around here. There's also an output of 4. Something happens with an output of 2. I can't really do much with the infinities, but it's good to be aware that they're there. So not much on row 2. But you can do something with this one. This is a particular limit where, because there's an infinity right there, and because there's a finite number right there, this one leads towards a horizontal asymptote. It's at height -4, so it's a really good idea to just plot that one right away. Let's go down 1, 2, 3, 4, and here's our horizontal asymptote. Okay, let me undo the highlighting. So we did the most critical step, folks. We looked before we left. Now we're just pretty much going to go down the line, down a portion of the sketch for each one of these instructions. I'll sketch the actual function in blue. And the first thing we do is we need to put something at f of 0 equals 3. That one's just going to be a solid dot, one single point. Input value of 0, output a value of 3. So that's one down. I'll check those off as we go just to make sure we didn't miss anything, and then just keep on going at it. Now we're dealing with the limits, but these are not the nice limits. This one is a left-hand limit. This one is a right-hand limit. So if we're going to focus on this one first, might not be a bad idea to just take a note card or something like that and cover up the whole right-hand side of the graph, because we only care about what's happening towards the left. As x gets closer and closer to 0, but coming in from the left, we have to approach a height of 4. So let's make that happen. First thing I would do is, if we're approaching a height of 4, it becomes extremely critical out of nowhere to put an open circle right here. We're trying to avoid a failure of the vertical line test by just preempting it. Make sure there's a circle, no failure. Then just let the curve approach that height, and we're all set. That's our first limit down. Does that make sense to folks on that limit there? Awesome. So it's saying, if we look at it, as x gets closer and closer to 0, only coming in from the left-hand side, f of x has to be getting closer and closer to a height of 4. And so we went like this, coming in from the left, make it approach I didn't mean to right-click on it, make it approach a height of 4. That was so fun, we'll just redo the whole thing with this one. This time x is heading to 0 from the right. That means the left-hand side of the graph is irrelevant. Sorry, participants, we'll put you there just for a moment. With the participant window, it's coming into a height of 2. So let's put in an open circle here as well. And there's a lot of different correct responses. Some people might do a horizontal line. Some people might go a little bit fancier and make it squiggle a little bit, maybe something like that. I wouldn't go too fancy. That one looks a little bit suspicious. Or you might let it come in like this. Really up to you. Just has to pass the vertical line test and satisfy that limit at the same time. And as you do these, it's a good idea to just imagine this. Check these out as you go. So you could do maybe with a note card, block that out. Look at the limit again and look at your graph. We're coming in from the right. Well, that means we're over here. We're getting closer and closer to a 2. If you notice you're putting in the same value that was there after you kind of just ignore it or put your thumb over it or something like that, then you're doing the same thing we did over here, which is far, far easier. You're grading as you're going. And that's a great strategy for getting through this kind of problem. The limit looks right as you consider them one at a time, then you're in great shape. So that's first row down. Now we're just going to redo the rest of these. This one is saying that as x heads towards the left, going towards negative infinity, the function goes to negative infinity as well. So you can do something like this. We're heading to the left, and it's eventually just going to dive bomb. For this one here, let me just, for the sake of making it clear why this is there, let's write out lim x goes to negative infinity, f of x equals infinity. You absolutely don't have to do that on your work, whether it's a quiz or exam. I'll sometimes do this on the notes just to visually show that's where this limit that we're checking off actually went. Well, that one's done. Next, we're going to deal with something around 4.
I do have a quick question.
Go ahead.
So if we were to do this on an exam, would we need 2 separate lines for the limit of f of x equals 4 and the infinity, or can we draw it like that?
So a different line for, you're saying this infinity right here and this one
Yes,
right here?
or the one above. So you
Or,
kind of connected it to the open dot on 4 and down.
oh, I gotcha. Yeah, I see what you're saying now. So the only reason we had to go to this open dot right at 4 is because it specified this limit right here. So those two had to go together with each other.
Okay, I see.
Awesome. And that's one thing that's kind of weird about these is there's sometimes is a lot of choice on what you get to put and where you place them, but sometimes there's very, very little choice. This curve had to directly go into that location to make that one true. Does that answer your questions about these so far? Any other questions at the moment?
Actually, yes. I was just wondering where we got the asymptote from.
Oh, that asymptote, good question. Let's put just an extra description. This asymptote was at height y equals -4. There's that -4 there. And its actual location came from this, and also the fact that it said x towards infinity. So both the portions highlighted in green right here and right here were required to get that horizontal asymptote in that location. Does that make sense for that question there?
Yes, thank you.
Yep, you betcha. And these are definitely pretty kind of tricky questions. We've gotten 4 particular evaluations down. 3 of them are limits. Now we're off to the single-sided ones. Any other questions or comments at the moment? Okay, let's give these a try. The thing to notice about these single-sided limits is that they output infinities. Both of these limits don't exist, and they're telling us the way in which they failed. But because they're outputting infinities here and here, these ones would lead to vertical asymptotes. Well, looks like just one because the input is a 4 here and a 4 there. Well, let me highlight the same way we did with the one in green. Because this time we're heading towards a finite number, but we got an infinity, same here, finite and infinity. Those are the ones that lead toward the vertical asymptotes. So let's put them down. I keep saying vertical asymptotes. It's just one because it's a double, or excuse me, a single-sided limit here and here. But here it is. That's the vertical asymptote. its equation would be x equals 4. And I'll highlight this one in yellow to say that vertical asymptote exists because of this. One or the other is enough to cause it. Now let's give this one a try. It says your x is tending towards 4. With the negative sign, it means only coming in from the left. So you can feel free to ignore this entire right-hand side. But when it does that, it's plummeting, heading towards negative infinity. So we can make our curve do something like this. That would be enough to say, yes, we're heading down towards negative infinity on this portion right here. Put a quick check on that one. And let me circle this just to say this one was lim, x tends to 4, but from the left, f of x, head towards negative infinity. Again, anything in orange is meant to be extra information on the notes, not something expected at all in your homework or your quizzes or exams. Looks like we have 2 more limits to go. Any questions at this stage? Okay, well, last one is kind of the same as the prior one, right? This time we're heading to a 4, but from the right-hand side. Instead of plummeting, it's blowing up towards positive infinity. And so you might draw something that goes like this, but let's get the right color pen going. So that's the one heading off towards positive infinity. I don't like the way I drew that right there, but let's go with it. Last limit is this one. X heads off to positive infinity, but then it approaches a horizontal asymptote at height -4. Let's see if we can make that curve do it. Oh, that was the eraser. Let's try again. So we need to take this curve, make it come down in a way that makes it believable, like it's a horizontal asymptote. What we can't do is something like this. That just looks like it fails a vertical line test in a very, very spectacular way. It looks vertical. I kind of painted myself in a corner, making it turn up, but as long as you make it come back down, you're okay. Try to avoid vertical lines is the only requirement. It looks a little sketchy right here, but that's okay. Doesn't have to be perfect if you're picking up your pen and plotting it again. I just assume that's one curve if you drew it out like that. But looks like we've got it, folks. That is all of the limits of this problem so far. Definitely a tricky one. We'll have opportunity to practice this multiple times. You'll start to see this in section 2.5 as well. We'll take a look at this kind of problem. Well, any questions or comments at all, folks, on this overall conclusion here? Okay, as mentioned, sometimes when you do this kind of problem, it might not be a bad idea to get, I don't know what it would be, maybe note cards or maybe stickers or something. Black these out. It's a little bit easier to do digitally. But if you black these out, you can now reverse the whole problem. Here's your curve. Find out what all the outputs are for all of these. If you're getting the same values, then that's an indication you really nailed your graph. You've got the right stuff. Well, I think we're ready for the next problem. And the next problem, like we mentioned, is more of a segue type of problem. 2 of these are assigned in WebAssign, and they are kind of tricky. Well, it's not that they're tricky. What's the word? They're tedious. So I felt like if I'm assigning something tedious, we should do 1 too. So this is almost a direct replication of how it would look like in WebAssign. The reminder here is to remind us, we're not going to do this every time. In fact, if we try to do the limit this way every time, we're not going to get very far in the course. That's a hard way to do limits, but it's a good way to segue into the next section. So let's give this a try. It says, guess the value of the limit, if it exists, by evaluating the function at the given numbers, correct to 6 decimal places. These instructions are pretty specific too. When they say that, that means we're not trying to round. We're going to just grab those 6 digits they give us. It's essentially rounding by truncation. No rounding to a nearest digit. Let's take a look at the limit. We have a rational function. X is heading towards +2, and we're going to evaluate the limit at these particular values. I just noticed that these are duplicated. That's kind of silly. Well, that's okay. We can, if we really want to, change this a little bit, but I think it would be okay to just leave it like that instead of changing the problem. Because we're taking a limit as x is heading towards 2, Best way to guess the limit is, well, this is a double-sided limit, right? We need to start at values above 2 and get closer and closer to 2 from above. And that's what this column is doing. Then we need to start from values below 2 and go up and up and up, getting closer to 2 from below, and see what values we get here. Now, if the limit exists, then the outputs here should be getting closer and closer to the outputs here. It shouldn't matter what side you approach to get the right value. If the limit doesn't exist, either the numbers here are getting wild, or they have nothing to do with the numbers here. The left-hand and right-hand side limits are different in that case. So now it's a lot of work. And what you could literally do is grab a calculator, get your 2.5, plug it inside here, and just crank it out. That could take a good amount of time to get through. That would make your WebAssign assignment pretty long. And so another reason I brought this one to class is I encourage you to try out Desmos. It makes this a lot faster because you can define a function, and the problem is nowhere near as burdensome. So here's how I would personally answer this question if I was doing this as a student. We need to import that right there. There's our function. There's a lot of ways you can do it. You could write y equals and just type it in. But for our purposes, we want to use and abuse function notation. So let's initialize it with function notation. F of x is going to be defined by, for the fraction bar, start with the slash button right by the question mark. Then just start typing things in. X squared minus 2x, x squared minus x minus 1. So there's our rational function, graph on the right if we'd like it. It looks like the limit should exist. Let's take a look. It looks like it exists, and it looks like it's 0, but technology is flawed. It's possible to write down certain functions where graphically it looks like we have a limit, but it's actually the totally incorrect limit. Functions can be weird. So we're going to work this out very carefully here and see how it goes. However, we might suspect, if we're giving a guess, I would guess the value of the limit is 0 based off just that graph. But let's see what happens with the function outputs. So now actually, we can save a little bit of time here by just a small window adjustment. Okay, I think I'm all set up. So now let's begin. So F 2.5. You can type that in directly, get a value out. And it wants 6 digits, and it says accurate to 6 decimal places. So we'll just copy in 0.45, 4545. So F at 2.5 outputs to this value. Now we go to 2.1. Here we just write that in. It updates immediately for us, kind of reminiscent of Excel. This would be pretty easy to do in Excel as well, if that's your preferred environment. Then the digits go 0.160, 305, if I'm copying those in. I'm actually really bad at copying, which is strange. So let me know if I copy in them incorrectly. We'll correct the record right away. So as we get closer and closer to 0, the outputs, or I said that wrong, let me try one more time. As we get closer and closer to 2, these outputs here appear to be getting closer and closer to potentially 0. It's already close to 0 on the second step. Now let's try it 2.05. At 2.05, we're closer to 0 still. This one's going to output to 0.088, 937. Then rinse and repeat. We kind of know the name of the game. For taking the limit as it tends towards 2, the one thing we can't do is plug in 2, because the function value is irrelevant to the limit. It may or may not match. So we're getting as close to 2 as we'd like to get a precise guess. So now let's add an additional 0 here. It went from about 900ths to about 100, so 0.009. 876. Again, accurate to 6 digits means copy, rounding by truncation, essentially. Then on the last step, it's 2.001. Let's change that to a 1. And we now have a 0.001995. And certainly as we got closer and closer to 2, the outputs themselves, they do look like they're getting closer and closer to something. If I had to guess the value, my guess at this stage would be 0. But that is a truly flawed guess. Because we know functions, they don't have to match on the left-hand side and the right-hand side. So we need to take a look at this again from this side and see if we're still heading towards 0. It is possible to write down a function where it's going towards 0 on this side and going towards positive infinity, say, on this side. So that's kind of unfortunate. It looks like on this problem that shouldn't happen based on the graph. But because graphs are flawed, we'll take another look on this side of the graph or problem. So now we're taking a look at, as we head towards 2, but now from below. Start off with the 1.9, and we're getting negative values. Well, we should expect that. We're approaching 2 right here, but from below means we're starting below the actual x-axis. We're getting values below. So it's negative 0.267, 605. Our hope, however, is as we go further and further or closer and closer to 2, these looks like they're always going to be negative, but they should be approaching 0 themselves. So let's add 0.05 to that, 1.95, outputs to this value. But question first in Zoom. $369. Okay, well, let's try this again. Next one is 1.995, so just include an extra 9 here. This one is negative 0.010126. At this stage, I think we can guess, it looks like the value is 0, but let's finish off the problem and see what happens on, oh, this is the weird one. What happens on the next values? I must have misformatted this one. 1.995 appears twice. Let's just skip over that one. That was a really odd typo. Sorry for that distraction. Let's go to F at 1.999. At 1.999, yeah, that's pretty close to 0. Negative 0.002005. That's 6 digits. So now we can kind of zoom out on this. Here's what happened when we evaluated functions around 2, getting closer and closer to 2. All of the output values seem to be approaching 0. And I really have to say seems to be approaching 0. It's perfectly conceivable that the right function is actually approaching, maybe it's 0.0005678, something random like that. Functions can do just about anything. But if we're going to make a guess based off this numerical evidence, here's what we would say. The limit as x tends towards 2, whether we're coming from above, like on the right column, or from below, like I said that weird. If we're coming above, like on the leftmost column, or from below on the right-hand column, the limit of that function, I'll just generically call it f of x, is equal to, by method of guessing, looks like a 0. How do folks feel like about that? Does that make sense on the process here? Awesome. And doing limits like this, again, it's not the worst thing in the world, but it does have its own big problems. It's hard to do this, even taking advantage of Desmos. That's a good amount of work. It's also flawed. There's no reason to assume that this must be correct. It could be some other value. And if we want to get exact answers, this at least gives us some intuition of what the limit should look like, what it should do if it does exist. What we'll be doing next is turning this around and show how to do this limit much faster, just using the ordinary limit laws. But looks like we did it, folks. That's the conclusion of these notes here. Any questions or comments before we go off to the next section? Okay, so at this stage, we've done a lot of work on limits. Section 2.4 is the same type of concepts, but we're looking at it from the algebraic side. And then section 2.5 is where we're going to look at continuity. After we're done with that, we'll finally be about ready to define the derivative in the next chapter. But the derivative is defined in terms of limits, so our best thing to do at the moment is take a look at these again. Well, here are the limit laws. There's more than we saw on the first day of class, section 2.2. This is more of a full set, and it is a lot of information, but I do want to say right away, our exams are closed notes, but I do provide documents on the exam as well. And this particular limit laws, these ones specifically, will be on an exam. So these laws are provided on exam 1. The goal of these laws is to kind of use them implicitly. Think of like your exponent laws. When we get really fluent dealing with exponents and all the exponent laws, we don't cite an exponent law like something along these lines each and every time we use them. We just know through the laws what we can do. Our goal is to get to the point where we take all of these for granted and we use them automatically. But to get to that point, we should see what we can use automatically. And before we get too far on that, these limit laws do have another additional feature we have to be careful with. We hinted at this before, but the assumption is for every one of these limits, through limit law 1 all the way to the bottom, the original limits here and here both exist, meaning we're also excluding this behavior. If you've got plus or minus infinity anywhere, those outputs means you cannot use that limit anywhere in any of these limit laws. That's a limit that does not actually exist, and it breaks down in the laws. But with that out of the way, here's all the limit laws say. And you can compare them very closely to the original limit laws in section 2.2. Only difference is we're heading towards a finite number, so it doesn't say x heading towards infinity here. Aside from that, it's essentially the same exact law. The limit of a sum of a function is the sum of the limit of the functions. Same with the difference, same with the product, same with the quotient, as long as you're not dividing by 0. Other great stuff like limit of a constant times a function is just the constant times the limit of the function, and so on. So what we'll do is we'll cite some of these limit laws as we go through the problems. And let's see a couple of them that are a little bit exceptional. I did want to point out, really impressive limit laws would be stuff like this one. Let's see what else. This one's also pretty impressive. Limit law 10, limit law 11. I would say for all those limit laws, maybe not as much limit law 11, let's take that off. Limit laws 6, 9, 10 are direct substitution properties. What we mean by that is, when we look at this limit law really carefully, all that's essentially happened is where the variable x was, we took where x is heading towards and directly, we didn't directly put it in there. We put the limit inside the whole function on this one. And on here, this is where we directly substituted a, right where x was, to get a to the power of n. Likewise, a directly substituted here to get the nth root of a, and so on. And that's kind of an interesting set of properties. Later on, we're going to call these properties about continuity. So there's the limit laws. And for example 1, this one is purely through a graph. We mentioned we're trying to get out of that, but the purpose of example 1 is just to get a little bit more familiar with these, and then we'll start using them in more directly. So we have graphs of 2 different functions given, f of x on the left, g of x on the right. And it says the graphs of f of g are given. Use them to value each limit if it exists. If it doesn't exist, we'll try to explain why. Let me know if I forget like I did in that prior section. And if the limit law is used, then cite the law used. That's not an instruction I'm going to put on any quiz or exam. This is more for us getting comfortable with limit laws in class, that last bit there. So again, let me pull these down. I'm going to delete them in the moment, but we'll use these to paste in the limit laws when we saw we used them. Maybe drop them. Oh my goodness, that broke that formatting pretty badly. Let's drop them there. And now we can get started. First thing you might want to do is color coding is not a bad idea here. We're dealing with multiple functions. Here's our f of x function, g of x function. I'll go blue and green with them. And the first problem, we're taking the limit of f of x plus the limit of g of x. That means we should be using, let's take a look, limit law number 1. That's the one that deals with the sum of functions. I'll put above here LL1 to say we're using that limit law. The actual step-by-step work is not too bad. First, you break up the sum of the limits into this thing, limit as x approaches 2 for f of x. Oops, sorry, struggling with the eraser tool. There we go. Then go plus the limit as x approaches 2 for g of x. So we did it, folks. That's the new content. We've gotten through the limit laws. All we have to now do is actually calculate out these limits. Still following the color coding. Any volunteers for what the limit should be as x tends towards 2 for f of x function?
One.
Yep, absolutely. Oh, sorry, I misread that. You're just about right. It looks like it'll be a -1. So I'd say that's correct in spirit. As we head towards +2, we're here, that's 2. On either side, we're down towards a -1. You know, honestly, the more I look at these. Oh, gotcha. Yeah, the whole thing, I bet you're right. But for this first part, we're going to get, let me just make those axes bold because that actually tricked me on this one. We've got a 2 here plus, anyone see the limit for g of x? Oh, hang on. Before we look at g of x, let me try one more time. As x tends towards 2, we're heading towards -1. I got to put that in incorrectly for no apparent reason. Must have been a micro sleep. But any volunteers for g of x, what should happen? Absolutely. We're heading towards 2, same value. And that means, well, on either side, the curve is getting closer and closer to a height of 2. That means we're done. And as you mentioned earlier, the limit evaluates in total to exactly 1. And now the whole work is complete. Any questions, folks, with that one there? Okay, that's the wild world of limit law so far. Doing this one here is not anything new. Let's see, how did we format our limit laws? It's really technically a brand new one, but sometimes with these limit laws, here's how they might be stated. It could have been a plus or minus here, plus or minus here, and then you could just eliminate that limit law entirely. And that's what your limit laws could look like. It's really the same thing rolled into one, but our author decided to break it up, so we're going to break it up as well. Limit law 2 deals with the difference as opposed to the sum, but it works in the same kind of way mechanically. This is limit law 2. First thing we can do with that limit law is break up the functions. We have limit x tends towards 0 this time, starting with the f of x function. Here's the limit law step. Minus goes right there. Now we're done with it. They go pretty quickly. Then it's going to be limit x tends towards 0 for g of x. Like before, we just go to each individual graph to resolve the limit. First one is asking about f of x, so we're on this graph here. As x tends towards 0, on either side, we're heading towards a height of 2. So 2 on this one. Then minus, and now let's just do it again for g of x. Any volunteers for what should happen on this limit here? Turns out this one would not be a 3. This one's a little bit weird in a certain sense, right? It has options in some sense. Anyone in Zoom see what the trouble could be with that limit right here? It's definitely kind of a nasty one, just out of nowhere, right? So let's take a real close look at this one. Put in some additional space. Oh, that will not work. We'll deal with the space we have on this. Oh, here we go. And let me start by going like this. We definitely have a problem, right? The problem is relative to that limit. So let's look at it really closely. As x tends towards 0, we have issues. There's two different values we could approach. And you might write out this. As the limit as x tends towards 0 from the right of g of x is calculated, that's a limit you can do. You're coming in from the right. It's settling down to a height of 1. Next, lim as x tends towards 0 from the left. That one's heading up to a height of 3 altogether. And this information alone is enough to say the limit as x tends towards 0 of g of x does not exist. So DNE on this one. Let's define it here just for a quick reminder. So this limit for g of x does not exist. And if your work ended right here, I would probably give full credit to that, but let's be really specific. If one part of your limit statement, say the g of x part, didn't exist, the entire statement that was written down does not exist. Everything is ruined as soon as one portion is undefined, essentially. So we can say lim x tends towards 0, f of x minus g of x does not exist. Our explanation for why it doesn't exist is really everything above what happened to g of x. It has different values depending on how you approach. But for a double-sided limit to really exist, these single-sided limits had to agree. So I don't know where this one looked a little bit tougher, but we got through it. Any questions at all with that one, folks? Okay, now there's another good reminder for this kind of thing. This is a particular type of discontinuity. Anyone recall which discontinuity this one is? Exactly, this is the jump discontinuity. Jump discontinuity. And the statement I want to make here, let me see if I can fit it in anywhere. Geez, that's going to be hard. Let's make it right here. When you have a jump discontinuity, the limit as x tends towards 0 of g of x, let's make it bidirectional, so this is if and only if, does not exist. You have to do the single-sided limits to get a limit that would exist the moment you have a jump discontinuity. So these are rough discontinuities for the purposes of dealing with limits. Unless you spot them, then you know that's a trickiness we'll get to and work around. Okay, well, we've done 2 limits. I hope the next ones aren't too bad. I don't think they are. Let's give them a try. This one is a product of 2 functions. There is a limit law for that, but let's see if we can find it. The product of functions limit law is this one right here, limit law 4. It says the limit of a product is a product of the limits. So you can transfer your limits in that way. Let's actually show it right here, limit law 4. Still as before, we have 2 functions, f of x and g of x, so I'll use the same color coding. We'll say it equals the limit as x tends towards -1 for f of x. We put in just a little bit of space. I personally use parentheses for this kind of product. I think it is a little bit more readable, but it's really up to you as a stylistic choice. And next one will be limit x tends towards -1 and for g of x. So like limit law 4 stated above, if you have a product of functions here and you're taking the limit, just take the product of the individual limits and you're going to get the right answer. That's a pretty amazing process. But now let's see what happens. This is relative to -1 on both of them. So if you're here on -1, we have a different kind of discontinuity. This one's called removable. Well, although it's a removable, we can still deal with the limit on this one. Anyone see what the limit as x tends towards -1 should evaluate to? Is it 1 or is it 3?
It's one.
I agree. In class and over Zoom, absolutely, the value should be 1. Good call, folks. And again, here's the thought. When it comes to taking limits, the actual value of -1 is irrelevant. Imagine the graph like this. Imagine that line's a little bit thicker. Doesn't matter where the open solid circles are at all. They could be totally, completely undefined or redefined in different ways. But as you head in from the left-hand side, it's approaching a height of 1. Head in from the right-hand side, it's coming down to a height of 1. That means the limit overall, as folks said, is 1. Definitely kind of a strange process. That's why we're looking at so many graphs to get a feel for it. But any other questions, folks, on this limit here? Okay, so it was a glorified multiplied by 1. I should probably fix this pen here. Let me try again. Now let's move over to the one for g of x. So we're heading towards -1. That means we're avoiding 0 in the jump discontinuity. We'll have an output here. So now at -1, this is continuous. It's at height 2. Whether you came in from the left or the right, that's going to be the outcome on this one. And if there's no holes, jumps, or anything like that, the curve looks like it was drawn in a smooth, continuous way without ever lifting up that pen or pencil. Pretty much, you're just directly substituting -1 inside the function g of x and getting that height of 2. So continuity and direct substitution go exactly hand in hand. Well, we did it, folks. The whole limit comes out to 2. Really, the main work was to break it up with the limit laws, divide and conquer, and just multiply 1 by 2. We have a few more to do just to finish off this problem. Any quick questions or comments on getting through these first 3? Okay, let's scroll down. Take a screenshot of that graph so we're not craning our necks looking up and down a bunch. And here it is below. We should probably take this to a new page just to make sure we can put in all of our comments we might want. And so same exact instructions, same functions below, but different limits. Here we're dealing with a quotient of limits, but that's got to be a limit law. Let's take a look. That would be limit law number 5. If you take the limit of a quotient of functions, just take the quotient of the limit of those functions. You can turn it around just like that, divide and conquer just like with the product. Only requirement is when you take the limit of the denominator, it cannot obtain a value of 0 or else we divide by 0. So that's how limit law 5 goes. Let's state it here. This one's limit law 5, and on paper, will become a pretty big fraction to start. Limit as x tends towards 3 for f of x in the numerator. Then limit as x tends towards 3 for g of x in the denominator. So now that's what we're calculating. And math is always amazing in that we made a good step of progress, but it looks like we made the problem worse. It's not worse, we're just focusing now on this end for f of x. We're heading towards 3, 1, 2, 3. No problems, there's direct continuity here. So the output should be exactly 1. So numerator is 1 for that limit. Then we just play that same game again, but you have to be careful with which graph we're using. This one's g of x, so go to that graph. We're heading towards 1, 2, 3. So that one outputs, well, that's not convenient, to a 0. Forgot what would happen to this one. Well, if you got that, there's a couple things you could respond. I'll leave it up to the class. Any volunteers for what to say after this? I agree. You could say just purely does not exist on this one.
And it's the g of x equals 0, right?
Exactly. That 0 there alone caused the problem. So we'll say here, because of this, the limit does not exist. And when it says explain why your limit does not exist, this is good enough for me. Your explanation is sometimes just the computation itself. We produced a 0 down below. That was the one exception that we were not allowed to actually hit for that limit law. And so this one is a true does not exist. It might be a positive infinity, might be a negative infinity, something like that. So that one's down or done. Any questions, folks, on that limit law there? Okay, we're getting to the point where these are not new limit laws, but they're still kind of fun problems to get through. We're taking the product of x squared and f of x. So first, that's going to be limit law number 4 to do that product. So let's put that there. LL4. But we also have to take the limit of x squared on our next step. Let's cross that bridge when we get there. First, let's use limit law 4. We will get limit as x tends towards 2 of the first function, x squared. I'll leave this one unhighlighted. Then take the limit as x tends towards 2 for f of x on this function. I will calculate this way. Next thing we need to do is we need to know what happens to x squared as x gets closer and closer to 2. But if you think about that x squared graph, that's just a parabola. It's completely connected. There's no discontinuities whatsoever on a parabola. This one should have a direct substitution property. Let's see if we can find it. Let's see, it's not this one, but it looks like it's limit law 9. Limit law 9 says, if you take the limit of an nth degree power function, just take whatever a is, raise it to the nth power. We're directly substituting a inside n, in other words. So that's limit law 9 right here. That's a degree 2 power function. And so to apply limit law 9, all we do is we take the 2 right here, put it in for x. Now it's 2 squared, and that's our direct substitution. We directly substituted in 2 into the squaring power function. Definitely looks weird, but continuity is actually pretty great since really nothing magical happens. You just drop in the number. We'll be abusing continuity a ton in the upcoming problems to do limits as fast as possible. So that's one down. Last one we need is limit as x tends towards 2 for f of x. So let's go 1 unit, 2 units. For f of x, there is a hole there, but that's okay. That's a 1-point problem. The limit still exists, and it would be equal to -1. That look right to folks so far? Okay, at this stage we're pretty much done, but we still have to simplify our work. This is 4 times -1. So the resulting limit is -4 on this one. Last one, folks. This one's weird because it's conflating a function output with a true limit of g of x as x tends towards -1. We should take a look. What happens to -1? If it was a jump discontinuity, you could have just said does not exist. There's a jump discontinuity. So too bad it's not heading towards 0. This is a bona fide problem. First, let's resolve f of -1. That's tying back to some other work. At -1, we had a limit of +1, but this is the function value right here at height 3. So f at -1 turns into height 3 altogether because we're not taking any limiting process on that one. Ordinary algebra for it. Here we're heading towards -1 for g of x. So we're here at -1. We have continuity, so we just directly substitute the value of 2 for that limit. So 3 plus 2. And finally, that means this whole thing resolves to a limit overall of 5. And now we did it, folks. That's the end of these limit laws right here. Really, the big takeaway again for this particular example is we're looking at the limit laws, seeing how they could be directly brought into a problem. We won't have to write out or cite the limit laws directly each and every time. Well, any last questions, comments, folks, on these problems so far? Good question. Let me double check. Oh, that was f -1. So 1, 2, this one was at height 3. This is just a weird scale. I would have liked if they put more digits or bolder axes on it. But other questions at the moment? Okay, well, looks like we have just enough time for a pretty exciting exercise next. We're going to take an honest limit using limit laws, no graphs whatsoever. So these are the bigger problems that are going to get us in the direction of defining a derivative. deleting all these because they're still there. This was just a quick copy and paste. First thing we need is the good old direct substitution property. It is powerful, but for the moment, it's only stated for two kinds of functions, the polynomial functions and rational functions. And it's a requirement that when you go to use this, as x tends towards a has got to be in the domain of that function f. So pick any polynomial, any rational function. If you take the limit as x tends towards a, you're plugging a into the function. The whole limiting process is just a function evaluation. It says, in other words, that's a class of functions where nothing new really happens. So we're going to later call direct substitution continuity. That's a good reminder because that's what continuity does, allows you to directly substitute. But the problem now with this particular property is we need to know what a polynomial function looks like and a rational function. And so this is a really fast example too. We're just putting down some examples of functions. I'll go first for a polynomial function. It could be, say, f of x equals x squared minus x plus 1. That's a nasty polynomial, doesn't look fun to factor, but it's a true and honest polynomial. Another one could be something like this, g of x equals 4. That's weird, right? It's just an ordinary integer, but you can think of it as a polynomial because you could always write in this, 4 times x power 0, for an example. That's just really weird for people to do that. So on this version right here, this is a degree 2 polynomial. For this version right here, this would be referred to as a degree 0 polynomial. Degree isn't super important, but occasionally people refer to the degree when they say the polynomial. So it's just good to know what's being referred to. So those are some generic polynomials, kind of low degree. Any example or questions about them so far? Okay, let's do a direct substitution property right away just to see what this statement is saying. If you take the limit as x tends towards something nice, let's tend towards 1 of x squared minus x plus 1, it looks like it could be a bad limit, but I mean, we don't have a graph, we don't have much to work on. But if you know that that's definitely a polynomial, think about your shapes of polynomials. They were always continuous. There was never any trouble doing those limits. You're just going to take a 1 and substitute it inside. It'll turn into 1 squared minus 1 plus 1. So the whole value of that limit is 1 after resolving all this simplifications here. You couldn't ask for a faster limit. I mean, that's even faster than doing it with a graph. I don't have to look for weird issues, jump discontinuities, removable discontinuities. It's just normal algebra is what it looks like over here. So we want to do the same with rational functions. Let's put down a couple examples of those. Any questions first, folks, with our part A?
Yeah, how exactly did you just get the second line of that?
On this line right here?
Yeah.
Pretty much all I did was I took this 1
Oh,
and
and
everywhere you see
substitute.
it. Yeah, exactly. Just was substituted right inside.
Oh, okay, thank you.
Yeah, you bet. Other questions so far? Okay, thanks for asking about that one. Now let's try some rational functions. Rational functions are really just ratios of polynomial functions. That's why we call them rational. So, well, one really weird rational function could be this one. That is rational. It doesn't feel like it. We just called something like that a polynomial function, but you could always write 7 as 7 over 1. That's a degree 0 polynomial in the numerator, degree 0 polynomial in the denominator. So you can think of a constant function as a true and honest rational function or a polynomial function. But in all honesty, when people say rational functions, they're usually thinking of something more along these lines. Say f of x. My control Z is bugging out. F of x equals, maybe it's say an x squared minus x plus 1 divided by x minus 4. Just a random polynomial in the numerator, a random polynomial in the denominator is all it takes for you to have a bona fide rational function. Now for these, again, if you know you have a rational function, you're in really great shape. But watch out for, let's see, one part of the statement is tricky. That part's right here. Let's suppose that we were doing this problem. Limit as x tends towards 4 of x squared minus x plus 1 divided by x minus 4. We have a really weird issue with this one. Out of nowhere, that 4 is an excluded value from the domain of this function. You cannot take f of 4, you would have divided by 0. And we do know a limit shouldn't depend on one single point, but we're working this through a technical theorem, and that theorem was proved with the requirement your a value came from the domain. It did not come from the domain here, so this limit does not exist. I don't know the particular way it doesn't exist. It might blow up to positive infinity, come down to negative infinity, but this one does not have an actual value. If you did it instead this way, limit as x tends towards, let's do a nice number, 0, for x squared minus x plus 1, x minus 4. This time 0 is in the domain of this rational function. It only had one value excluded from the domain. That was positive 4. So the direct substitution property does work on this one. And the work would look like this. As x tends towards 0, because the function is rational, we'll get 0 squared minus 0 plus 1. Down below, directly substitute even more, 0 minus 4. And so the whole thing will turn into a negative 1/4 altogether. So that limit's really fast. I mean, the one above is fast too, as soon as we recognize x tends towards 4, where 4 is not in the domain, gives that does not exist. But that's some of the limits that we're going to be calculating shortly as we go through these notes. Also, as we go through these notes, one of the major things we want to learn how to do is how to get around that when the limit might actually exist sometimes. It didn't have to go off to positive or negative infinity. It's possible that you can't directly substitute, yet the limit does exist. We'll see those examples in these notes. Well, let's see, we've got about 7 minutes and some change. I think we have just enough time to go back to direct substitution property and try out a couple examples. This time we're not worried as much about writing down an example of a polynomial or a rational function. We're just looking at various values like these. But I do have a note here that says for full credit on quizzes and exams, we do need correct limit notation. We have to say what we mean, we have to mean what we say. And so I'll try to make a mention of that as we go through these limits here. Correct limit notation for these problems is not so bad. You have to start with a limit statement, but the problem would, or else the problem is flawed. If it had start with limit as x tends towards 0, that's a rational function and 0 is in the domain. And you know what? That one is like deja vu. I forgot I did this. That's the one we did very, very painstakingly in section 2.3. We might as well compare our work. I forgot that that was on there. We took the limit as x tends towards 2 of x squared minus 2x. Is that the right one? No, it's not. Divide by x squared minus x minus 1. And as we headed towards 2, we had a value of 0 on this one. Let's make one small change. Let's head towards 2 on this one as well. Just making it the same exact problem, but that's an edit, so I'll put that here in red. So we're going to evaluate this limit. And in using correct limit notation, the first thing you have to do is drop the limit statement. That's because we're throwing in the value of 2 inside the positions for x. The limiting process is over the moment you do that. So correct limit notation means no limit at this stage. We just write out the value, put in 2, square it here, minus 2 times 2. Then the denominator will be 2 squared minus 2 minus 1. All we've done is we've taken this 2 and substituted in for x everywhere x occurred. Then we now need to work this out. Let's try the denominator first. It's going to be 4 minus 3, so we get a 1. The numerator is 4 minus 4. So we have 0 over 1. That's not a problem for us. 0 over 1 is exactly 0. And now the whole problem is over. So when we did it the much more hard way over 2.3, we guessed a value of 0, and this is how we achieved it. But with the limit laws on the table, and combining with the direct substitution property, for example, this is all you really have to do. Recognize it's rational, 2 is in the domain, and then just plug and chug your way through. We've just satisfied that limit extremely fast. Any questions at all, folks, with that one there? Okay, let's try it out to another one. These go really pretty fast. This one looks a little bit sketchy, but you know, it's not too bad either. The first thing that would bug me as a student in this class is the 5 right there is kind of burdensome, but that's the limit of a constant times a function. Let's go grab the right limit law. If we use this limit law right here, then we have absolutely no problems with that constant of 5 emerging. Sorry, that's a lot of scrolling right here. So let's put it here just to cite it. This can turn into 5 times the limit as x tends towards -3 of the square root x squared minus 2x. So looking at the limit law, we had a constant times a function. So we took the constant times the limit of that function. And that's pretty much what that 5 did there, highlighted in yellow. Next thing we're going to take a look at is, well, hold on a moment. We have to be careful, right? The direct substitution property insists you have a polynomial or a rational function. That is neither a polynomial nor a rational function. It's a composition of a square root function and a polynomial function. That doesn't have a direct substitution property at the moment. This is why we need a bigger chapter on continuity. But what we can still do in just this section is, apologies for the scrolling, we need a new limit law. That was this one right here. Well, this one. It says if you take the nth root of a function, the limit of that, well, it's the nth root of the limit of that function. Limit law 11 will do the job. Let's pull that down. It's getting kind of exciting. I didn't recall that there was so much going on into that one little problem. Okay, here's our next limit law. So the limit law says, if you have an nth root, and we do, this is an index of 2. We have a square root. So that index of 2 is typically suppressed in this case. But that's okay. N just has to be even, and it would have to also be positive. So our n fits the bill right here, whether you wrote it in or not. Then the limit operator, and this is an amazing property of continuity, commutes inside your nth root. It's just going to go right inside there. Let's show that step right away. Let's show it in green as well. I think that's a tricky looking limit law. This is going to be equal to 5 times the square root of the limit as x tends towards -3 of this inner function, x squared minus 2x. Okay, so we've involved 2 laws. Limit law 3 took care of the constant, which was a distraction. Limit law number 11 took care of the square root, which is a major distraction. But now when we're right here, we're going to use this idea. Direct substitution property works if you have a polynomial. That is an honest to goodness degree 2 polynomial. You can directly substitute right at that position. We're going to take -3 and just plug it in, square it, and double it by -2. Kind of an adventure on this one. But when we get fluent with this, you might have noticed that really all we're doing is taking -3, putting it here, and cranking out the whole problem. We just haven't seen these problems a lot, so we did it step by step through the limit laws. But sorry, didn't need to scribble on that. Let's actually finish this one out. This is now going to turn into 5 times the root of. Correct limit notation meant we had to put a limit right here. We had to put it here, but now we're done with the limit. We're evaluating and we drop the limit statement. We're going to get -3 squared minus 2 times -3 At this stage, we still have to simplify the problem, so let's crank this out even further. Let's see, that's gonna be a 9, positive 9, plus 6. So we have 5 root 15. Hey, and bonus, that doesn't simplify. So we have a reduced answer already at that stage. But those were the limit laws right down below that we had to use to get this through. And then direct substitution all at the same time. Well, we did it, folks. So that's a good amount of work through already in this section. The section is pretty big, so we'll spend quite a lot more time in it when we're back to class on Thursday or Wednesday's class. We may open up continuity, but I suspect we'll still be in this document for quite some time. Any questions or comments at the moment before we call it a night? Okay, well, have a great night, everyone. Thanks for all the participation in class and over Zoom. It is definitely tricky, but we'll get better at it as we get more fluent with it.
Our quiz is due Wednesday, right?
Yeah, oh, thanks for the reminder. Yes, the quiz here is due on Wednesday. Quiz number 1. And before we come to class on Wednesday, that's when you'll see the next quiz posted as well.